Hi, welcome to a new lesson of our Quantum Optics course, Season 2. Today, you will encounter an emblematic example of what became possible with the progress of quantum optics in the early 1980s, producing new states of light with property impossible to understand in the context of classical optics. In Quantum Optics 1, you discovered the example of one-photon states of light. Today, you will learn what is a squeezed state of light and understand how such states allow one to beat the standard quantum limit. It means that it becomes possible to make measurements with a sensitivity better than what had been for a long time considered the ultimate limit, associated with photodetection shot noise. One must acknowledge, however, that the associated technology is very demanding, so there are not many applications. But there is a case where using squeezed light is worth the effort. That is, the amazing great interferometers used for detecting gravitational waves. Compared to the technological achievements necessary to build and operate these interferometers, implementing squeezed light is a moderate supplementary effort. In Section 1, I will present a detection technique, homodyne balance detection, which has been much developed in the context of squeezed light and which plays a major role in modern quantum optics. In Section 2, you will learn what are the quadrature components of the field in a given mode, first for a classical field and then for a quantum field. You will then see in Section 3 how these quadratures and the field itself can be represented in a very useful way in the complex plane. In Section 4, you will enter the heart of the lesson with the definition of squeezed states of light and their properties. In Section 5, you will have some general presentations of how squeezed light may allow one to beat the standard quantum limit. Unfortunately, squeezing is fragile and thus difficult to use. You will understand why in Section 6. In Section 7, you will learn how a particular kind of squeezed light, squeezed vacuum, can be used to measure phase difference in an interferometer with an accuracy better than the standard quantum limit. In Section 8, I will explain you how squeezed vacuum can improve the sensitivity of the great interferometers used to detect gravitational waves. In conclusion, I will insist that beating the standard quantum limit with squeezed light is a paradigmatic example of a quantum technology.